Today's lesson, 5.1a, is using the first derivative test to find critical points, max, min, and increasing, decreasing. If we sketch the function given in our calculator or plug it into our calculator, you're going to see a graph that is incomplete. And so we use the first derivative test to try to talk about parts of the graph that we cannot see. We're going to use the first derivative to determine where the function is increasing and decreasing. That'll be the first thing we do. So try to remember from what we learned previously that the original function is increasing when the derivative is greater than 0, which is positive. And it's decreasing when the derivative is less than 0, which is negative. So our steps to find increasing, decreasing using the first derivative requires us first to find the derivative. So 3x squared becomes, x cubed becomes 3x squared, negative 9x squared becomes negative 18x, and negative 48x becomes negative 48. The next step says to set the equation equal to 0. And you can see that both sides of the equation are divisible by 3. 0 equals x squared minus 6x minus 16. In factored form, that's x minus 8 and x plus 2. So our critical values are solving for x is going to be x equals 8 and x equals negative 2. Using these values, we're going to be looking at this chart here, which in the first row talks about intervals. The next row talks about the first derivative, and the last row is going to be what the derivative tells us about the original function. If you look at the intervals, you can see that they're broken up based on where we solved for x. So one interval is less than negative 2. The next interval is between negative 2 and 8. And the last interval is x greater than 8. We're testing to see where the derivative is positive and negative. So you can see here it says pick a point and substitute it into the first derivative. So we're going to substitute in a point less than negative 2, which is negative 3. You're going to get positive 33, and the sign is the only thing we care about because when the sign is positive, the function is increasing. So we're going to write increasing on the next row because now we're talking about the original function, and the derivative helped us figure out what's happening on that part of the function. For the next interval, we're testing a value between negative 2 and 8. So 0 is a good value to test. When you plug that into your calculator, you're going to get negative 48. Again, the negative is the important part. And when the derivative is negative, your original function is decreasing. Lastly, a value greater than 8, we can choose 9. If you already have your original function in y1, to plug in 9, you can do second calc 6, which I think is dy dx. And if you plug in 9 for the x value, your calculator will tell you dy dx, also known as the derivative, will be positive 33. Again, the derivative is positive, so the function is increasing. This means that when we plug f of negative 2 into our original function, there will be a maximum, because if you look at the last row of your chart, the function first increases and then decreases. When we plug 8 into the original function, that produces a minimum. because on our chart, again, in the last row, our function decreases and then increases. So using this information, solving for our x values when we set the derivative equal to 0, we can now do a more accurate graph where we can name our maximum, and we can find the y value that goes with that maximum by doing trace -2, and 108 will be the y value of the maximum, and then at 8, where the minimum occurs, when you plug in 8 into trace, it will tell you that -396 is the matching y value. X equals -2 and x equals 8 play a play a key role and are called critical points. Remember, if you just have the x values by themselves, that's the critical values. And when they talk about critical points, you want both the x and y value of each of those maxes and mins. Our definition of a critical point is for any function f, a point p in that domain of the original function, where when we plug that point into our derivative, we get 0 or we get a value that is undefined. If those occur, that is the definition of a critical point. If our function is undefined, when we plug p into the derivative, you cannot do a horizontal tangent there. If you remember previously when we were studying continuity and where points were derivative and where they weren't, the absolute value is a perfect function to see that at the vertex here, you cannot do a derivative. And so you could say that the derivative is undefined at that point, and the reason would be is because it's a sharp turn. Sharp turns, you cannot do a derivative, so you cannot do a horizontal tangent. Examples of critical points. In this example, we've got one critical point that's a minimum. For the second one, I would say not that there's none. You can do a horizontal tangent, but it is not a max or a min. It's a kind of critical point we'll talk about later. And when we have a trig function like sine or cosine, that's going to have an infinite number of horizontal tangents. Our local max and min are determined by figuring out where our graph is increasing or decreasing. So going back to our definition of a critical point, if we have a point P where the derivative is 0 at that point, so we can do a horizontal tangent. On the left, if we figure out that the derivative is negative, and if we do a point on the right of P where we find out that the derivative is positive, we can figure out that the graph is decreasing and then increasing, producing our local min. On the other hand, on the graph on the left, if we have a point P where if we plug it into the derivative, we get 0 as the value, it's a local max if at first our derivative is positive on the left and then negative on the right, in which case the graph goes from increasing, decreasing in the original function, producing a local max. So for number 2, going back to our original equation, if you remember, we had increasing and then decreasing and then increasing. And we know this because this is the same equation as we did in number 1. And when we have that, we can see from our graphs above that when a function is increasing and then decreasing at -2, this is the dividing line between the intervals, x equals -2 produces a max. When our function is decreasing and then increasing, happening at x equals 8, that's going to be a minimum based on our definition above again, because if it's decreasing and then increasing on the original function, that would appear as a minimum. Before we talked about when the graph looked like this, critical points do not have to have a sign change. So that means it does not have to go negative, positive, in which case the graph would be decreasing and then increasing, producing a min, or positive and then negative, meaning that our original graph goes up and then down. We can have a function like x cubed where every single slope is positive, but this point in the middle called an inflection point, and we'll learn more about that with the second derivative, still has a horizontal tangent. You can see that even though I can do a horizontal tangent lying on that point there, all of my derivative values in this graph are positive. So a function does not have to have a local max or min at every critical point. Sometimes we have a critical point that is called an inflection point. And one more example. I don't know why it's numbered 5. Looks like we're skipping around a bit. So for number 5, we have a function. It's also a cubic function. Okay, I figured out that I was on the homework and I didn't finish the notes, so I'm back to our notes again. We're given a function. This is from page 8, and we need the derivative because we need to set that equal to 0, and then find the critical points based on solving that derivative equation set equal to 0. The derivative is going to be negative 3x squared plus 12x minus 9. Set it equal to 0 to solve. Negative 3x squared plus 12x minus 9 set equal to 0. Both of these sides of the equation can be divided by negative 3, making the equation easier to solve. Two factors that multiply to 3 that add to negative 4 are negative 1 and negative 3. Solving makes that x equal 1 and x equals 3. Use those values in your chart to help you come up with the intervals. So our first interval is going to be between negative infinity and 1. Second interval between 1 and 3. Third interval between 3 and positive infinity. We're going to take values that are less than 1. Usually, as we said, we like to use 0 because that's just a little less than 1. When we plug that into our equation, we get negative 9. We are only interested in the negative sign. When we plug 2 for the second interval, because it's between 1 and 3, we get positive 3. And when we plug a value greater than 3, we can plug 4 into our derivative. We get negative 9. The negative is what's important. So we go decreasing, increasing, decreasing. And in terms of our original graph, it's going to look like this, where x equals 1 is our minimum. X equals 3 is going to be our max because now we're increasing and then decreasing. So again, this was the min, this was the max. Our critical values listed are 1 and 3. When we plug 1 into our calculator in the value function, our calculator will say the matching y value is negative 5. When we plug 3 into our calculator into the original function, the calculator will tell us that negative 1 is the matching y value. Our local max is going to occur at 1, so the max is going to be negative 1. These are the important parts of the max and min. Negative 1 at x equals 3. Local min is going to be negative 5 at x equals 1. Our increasing is going to be our interval here between 1 and 3. Decreasing is going to be negative infinity to 1, union with 3 to positive infinity. Our graph, according to our calculator, will look something like this. And we can label our max and min. Oh, that's a terrible graph, but My time is up, and I hope